Hi everyone, welcome to a new video. My name is Dani Foya and I'm the CEO of Flowhog. At Flowhog, we help companies to automate their internal operations using AI. In this video, I'm going to show you how we have built an AI listing manager that manages all of our listings in our directory. This listing manager is able to search the internet, find potential listings to be published, assign categories and tags. We have also incorporated feedback into the agent, so it's waiting for our feedback before publishing these agents to our database. We have built this agent using LangGraph and PydanticAI. So in this video, I'm going to share you the code and how we have built it. So this way, hopefully, by the end of the video, you'll have a better understanding of building this type of AI agents. There are plenty of frameworks out there. There are high-level frameworks like Crawl4AI. And on the other hand, we have low-level frameworks like PydanticAI and LangGraph. I have personally struggled to find the best framework to build AI agents until I found this video of Cole Medin. I'll leave it here. Cole is doing a very good job explaining how to build agents, so you should definitely check his channel. In one of his videos, he explained how to build agents using this combination of frameworks, PydanticAI and LangGraph. So after personally experimenting some frustration trying to build AI agents, I give it a try using this combination, and I have to say that it's very powerful. So on one hand, you can use PydanticAI to build very specific agents. On the other hand, you can use LangGraph to orchestrate all these agents. So at the end of the day, with these two frameworks, you have a lot of modularity. And what I mean by modularity is that you will be able to build very specific agents using PydanticAI, and you can tweak each of these agents independently without having to modify the other ones. And then with LangGraph, it's very easy to orchestrate them. So you can connect them and you can decide how the data is flowing between the agents. So with this, it will make it very easy to scale your system. For example, you can start building a very simple flow, but you can keep adding new agents without compromising the quality of the initial flow. With no further ado, let's go to the video. Before we have a look at the program itself, let's talk about the different frameworks that we are going to use to build the agentic system. First of all, we are going to use PydanticAI. That PydanticAI, basically it's a framework that it's quite low level and quite easy to understand. So for example, if you have a look at the agents, you can simply define an agent with not many lines of code. Then for example, it's quite easy to integrate new tool to these agents. As you see here, this is one agent with two different tools. It's quite straightforward. The next framework that we are going to use is LangGraph. And LangGraph, it's a bit more complex than PydanticAI, but it's a very good framework to do orchestration. So in our case, we're going to use LangGraph to allow the different agents to communicate among themselves. I don't want to spend much time here, but some of the cool stuff that LangGraph has, first of all, it's quite easy to create some memory for these agents. You can post the workflow and then you can later resume it without losing the state of the flow. And then the human in the loop. This is also a very powerful thing that LangGraph offers, and it's that at some point you can interrupt the flow and allow some human input before proceeding. The way LangGraph works is you have to define some nodes, and then inside each of these nodes you perform some actions, and then you connect these nodes with edges, and this way you define the flow of the graph. We'll later see the graph in our case, but this allows you to create very powerful structures. We're going to use a library called Crawl4AI. It's quite good to do scraping, and you can easily parse a website HTML into Markdown. And then for the user interface, we'll use Streamlit. There is an open source library in order to make a front end. They make it quite easy to integrate LLM apps. They even have some demos about how you can build a chat interface. And this is what we are going to use in our application. All right, so now that we have explained a bit the tech stack that we are going to use, let's have a look at the graph that is going to be our custom graph. As you see, we have 7 different nodes, and each of these nodes is going to be an AI agent built with PydanticAI. So the first agent is going to be a search agent that will be responsible for scraping the internet and trying to find potential listings that could be inserted in our directory. And here we are going to use Crawl4AI, and we are going to provide him some sources. So in our case, we use newsletters to find new listings. Then once this agent finishes his part of searching these newsletters and extracting potential listings, then we want to send this information to a second agent, that is the listing filtering agent. And this listing filtering agent will have some quality criteria, and will decide whether these listings that this search agent has provided him are of quality enough to be published in our directory. The good thing about this agent is that it will provide us a confidence score. So it will tell us how sure it is that a specific listing fits our criteria. Then once we have filtered these agents and we only have the ones that are of enough quality, we are going to go to the summarizer agent, and this agent will again scrape the website of each of the listings and will extract some summary in a format we want. For example, in our case, we want to extract a description, some features, use cases, and also pricing tiers, among others. Now that we have some information about the listings, then the listing classifier agent will be responsible for assigning tags and categories to each of these listings. Something very particular about this agent is that this agent will be connected to our database and will fetch the categories available in our directory and also the tags available. Here we will play again with confidence scores, so this way we can see whether the agent is quite sure about what he's doing or is not that sure. With these confidence scores, later we can decide whether we want to accept what this listing classifier has done or we want to change it. And this is where the feedback collector comes into place. This feedback collector node basically will be waiting for the human input, and then after providing the input, there will be a router. It could be seen as a very small agent that his function will be to decide whether the human has decided to modify some listings. In that case, it will redirect the flow towards the listing rectifier agent, or whether the human is fine with the information provided and the human wants to proceed to publish the listings in the database. So this way we'll route the flow towards the publisher agent. Something very interesting is that, as you see here, we have a recursive loop, and what we are doing is the flow will be stuck on this loop unless the human explicitly says that it's fine with the listings and that he wants to proceed to publish these listings. This is a pattern that it's quite used, and it's a very good safety measure because this way you have strict control of the flow and you only allow the publisher agent to modify the database when you give him the explicit consent. Okay, let's get our hands dirty and let's have a look at the code. I will first explain you the folder structure that we have in our project. Then I will go into each of the different files to explain you what's the function of each file. And finally, I will explain you how you can run this agent on your own. So if we have a look at the folder structure, we see that we have an agents folder, and each of these files represents an agent that will be run inside each node of our graph. I will later show you more in detail in the main graph file how we have connected the different agents. Then we have our Python environment. We also have a .env file. I will create an example of .env file so you can insert your environment variables. We have a gitignore file, a LangGraph JSON file, that this is a file used to run LangGraph Studio, and this way you can see the graph that I have seen you before, this one over here, and you can run it from here in order to do some debugging and see what's going on with the graph. I would say the most important file of the folder is the main graph, that here it's defined the different nodes and how each node is connected. Then we have a requirements file to install all dependencies. And then we have the Streamlit UI. This is the interface that we'll be using to interact with our graph. So this way, instead of going manually to the LangGraph Studio and trying to run the graph over here, we can create a nice UI and interact with the graph in a way that it's conversational. So as you'll see, we'll have a chat and we'll be typing things in the chat, and then this will trigger the graph and will also print the responses of the agentic system. All right, so let's have a look at the first agent. And if you understand this structure, then you are ready to go and build your own AI agents. And this is what I've done. Basically, all this structure that I have here is the same one in the different agent files, but just adapted to the functionality that we want for each agent. So the way we have built agents here is, first of all, you need to define the model, and we are using GPT-4o Mini. Here it's important that in your .env file, you expose an OpenAI API key. Then we are using a prompt, and here is the prompt for this agent. As said, we are going to crawl a newsletter called Neuron Daily, and we are going to extract potential AI agents from that newsletter, because in the end, in our directory, we list AI agents. This is a very simple prompt. We are providing what day is today. This way we can explicitly tell him if we want to extract potential listings from a specific article. With this defined, we can go to define the agent itself. And this is how you define an agent in Pydantic AI. You use this function that's imported from Pydantic AI, and here you pass a model, the one we have defined here. You pass a system prompt, And then you can optionally pass a result type. And if you pass a result type, the agent, every time that is run, will return the output in this type. And this is very powerful because this way it's quite easy to communicate agents between them. We are telling this agent to provide a list of tools. And for the tool, we're going to extract the name, the description, and the URL. Also, something to keep in mind when you are building the result type, it's important that you specify what is each field used for. And you do it with this field function. And here, the LLM will read these descriptions. This way, it will be easier for the agent to understand what's the type of output that you want. So with this, you have the agent defined. And then you can easily assign tools to this agent using this decorator over here. So you use this decorator with the tool plane. And here important again, maybe we can better see it here. This is a second tool. You want to explain to the LLM what is this tool used for, what are the arguments that it should pass, and what is the output of this tool. And this way, with this information, the agent itself will autonomously decide whether he wants to call this tool or not. So for example, here we have two main tools. We have one tool that crawls the neuron daily, and here we are just using this function that we have defined on top of the file. Here we are using Crawl4AI library that I explained before. This is a simple execution where we just crawl neuron daily. If the page is not found, that shouldn't be the case, we'll return a 404 error code. And on the other hand, if it's properly retrieved, we'll return the markdown. So then this agent, when we communicate with him and we ask him to provide new tools, he will use this first tool to extract the articles of the neuron daily, and then he will use the second tool to extract specific content from a specific article. So here we have defined our second tool that uses this function that accepts a URL. And again, the code is very similar to the one we have for crawling neuron daily. We are crawling the specific URL provided in this function. So now the agent knows that he has two main tools at his disposal. For the first tool, he just has to call it and he will return a string that contains the list of published articles in the neuron daily. And the second tool, if he wants to call it, he will need to provide a specific article URL, and this way he will be able to get the content of the article as a string and then use it to create the final output. And that's it. This is how you define the agents in Pydantic AI. And as you see, it's super cool because it's quite modular. So the way you define tools, it's very easy. You can also easily change the output you want. This is why I think that Pydantic AI is a very nice framework to build these agents. As you'll see later, we will import this agent into the main graph and we will run it there. So as we saw in the graph, the next agent is the listing filtering agent. So this agent is responsible for taking all these tools that the search agent has found and to filter those, so we only keep the real AI agents, okay? And here it's the same. We define a model, again the same model. We define a system prompt. Here in our case, we're explaining the agent his job, that it's a classifier expert, how should he decide whether a tool should be filtered or not. We are asking him to provide a confidence score, and we are providing him some criteria to decide what's the confidence score when classifying the tool. Something to keep in mind when you are defining this confidence score for the agent, you have to be very explicit about the different thresholds that you have for the confidence score. Otherwise, if you don't do this, the agent will just provide confidence scores that firsthand look quite good, but at the end of the day, you don't know the rationale of the agent, so it's the same as not having confidence scores. All right, so with this prompt, we can proceed to define the agent, and as we saw, we are going to do the same. We define an agent, we use a model defined here, GPT-4 Mini, we assign the system prompt, and for the result type, we want this agent to provide a class that we have defined as potential AI agent. For each potential AI agent, we want to return the name, the URL, the confidence score that I was saying, and then we might want the agent to return a reasoning. To be honest with you, this is optional, we could remove it, and this is more used in debugging purposes. So this way you understand why the agent has decided to filter one listing or not, and this way you can use it to modify your prompt according to this information. All right, so with this, we can now assign a new tool, and here we have a tool that is very similar to the one we have in the search engine, that is just crawling a specific listing. And it's actually the same function. We use the Crawl4AI library to crawl the URL provided as input. The only thing that we change here is that we are telling that instead of getting content from tools, you are explaining the AI agent that this tool will allow him to get content from a specific listing homepage. All right, so now let's proceed to the third agent in the flow. For the listing summarizer, he will receive a list of potential AI agents with a name, a URL, a confidence score. And then his job is going to be to extract the information that we want from this agent. It looks quite complex because it's a long file, but the logic behind it is the same that we have seen before. So we define a class model that in this case is AI agent listing, and we force the agent to always return an output of this type. We define a model, we define a system prompt. I'll now get into this, but let's have a look first at the overall structure. And then we assign tools. Okay, so as you see, it's similar. It's just that it's an agent that it's more complex in terms of prompt and also the tools it has. But in the end, the structure is the same that we have used. So for the prompt, here we are telling the agent that he will receive a set of listings, and then his job is to extract content from each listing and provide it in the following way. We want a name, we want a short description, features, use cases, etc. We also want to know if this potential AI agent is open source or closed source. In the end, this is a very custom prompt that we use for our use case, but in your case, it will be very different. And for the source type, we also tell the agent to provide a confidence score. And as explained before, we have to explain him a bit how he should assign a confidence score. The result type you see here, it's an AI agent listing with all these fields. We always provide the description of each field. So this way, it's easier for the agent to understand what type of information we expect in each field. And finally, we define a new tool. That this tool is quite similar to the other ones we have seen, with just one difference, and it's that in our case, we are also extracting the pricings of these listings. So what we are doing here is we are using Crawl4AI to crawl a specific URL that will be the homepage of the listing, but also we try to extract the pricing by adding a relative path to the homepage, and this way, and then we put it together. So as you see here, we are returning homepage and pricing. This is a very optimistic approach because many times this pricing page doesn't exist, but it's fine. If it doesn't exist, we'll just return a pricing page not found. So now the agent knows that he will receive a website link and AI agents, and he has this tool that allows him to get content from a specific AI agent page. So it will be clever enough to know that this tool will provide him the content that will allow him to provide us all this information. Okay, so the next agent in the flow, it's the listing classifier agent. That now this agent is responsible to assign tags and categories to each of the summarized listings. This agent, it's a bit different in what it refers to the tools used, because it will be connected to our database, and then it will be able to fetch the categories and tags that we are using in our directory. So we define a system prompt. Again, here it will be very custom for your use case. In our case, we are providing him the available categories in the prompt. So actually we are doing this here. We are running this function, get categories from DB. It connects to our database and extracts the different categories. And we define the model. In this case, it's also GPT-4o Mini. We are all the time using GPT-4o Mini. It does the job quite good, especially when you are decomposing a very big task into smaller subtasks. What I found is that 4o Mini works pretty well in these subtasks. If you are not asking more than 2 or 3 tool calls, GPT-4o Mini works quite well. If you are building a system that needs reasoning and it has to call tools several times, maybe 4o Mini it's not good enough. So the model, system prompt, the result type, this is a very bad practice because I've defined 2 classes with the same name and they are different, but this class is quite similar to the one that we defined in listing summarizer agent. But we are also adding the category score and the tags scores. Okay, so category score, it's here. It has a category ID from our database, a name and a score. And then the tag score, it's the same for the tags. We want to store this category ID and tag ID because this way, when the listing publisher agent comes into place, he knows what's the ID that it has to insert in our database in order to assign these categories and tags to the listings. But as said, you should never define a class name similar to one you have in another file, because it's quite easy to get confused and by mistake importing the type of class that you don't want. In any case, let's proceed. And then for this agent, we just have one tool, and that it's the tool to get category tags. So we explain him that this tool is to get tags for a specific category, and it should provide the category ID. Because then if we have a look at this function, it's connecting to our database and is using the category ID to select only tags that are used within this category. So with this, the agent knows that it has some set of categories that we define in the prompt, and here we are passing both the ID of the category and the name. And then he knows that to assign the tags, he will then first have to call the tool getCategoryTags and provide the category ID. And then with this information, he will then have to assign tags to the listing. All right, so now we have the final agent with all this information, and we have it classified. So the next node in the flow is the feedback router. This case is a bit special because before calling this node, we have the human in the loop interaction that we will later see in the main graph. I will explain it more in detail. But as of now, just think that this agent will receive some feedback and he will be responsible to do the task that is defined here. We define a very simple AI agent using Pydantic. We use GPT-4 Mini. And the system prompt is, your task is to route user messages either to the assistant that has to modify the listing information, this is the listing rectifier agent, or to the one that has to insert the listing information in the database. And we are forcing him to provide as output either rectify listing or insert listing. So for those of you that haven't built this type of systems before, you might be asking yourself, what is the feedback of the user, right? Because here we are just providing a static prompt. So how is this agent able to receive the feedback? And the way it works when you're building agents, you have what it's called a system prompt, but then you have a user prompt. So the system prompt, it's a base knowledge that you give to the agent about what is his behavior and what's his task or job to be done. And then when you call these agents, you will see that in the main graph, we are providing a user prompt. So we are providing some information, and this agent will first consider his system prompt, and with the system prompt, act according to the input that we provide in the user prompt. Now we have two more nodes remaining. The first one is the listing rectifier agent that we have it here. And remember that this listing rectifier agent, here, will come into place when the feedback router decides that it's his turn. Here, similar structure as always. We define a model, we define a system prompt. So I will provide the code in the description, so you can have a look at the prompt more calmly. But this is quite similar to the listing summarizer and listing classifier agent. We have done a mix. It is able to change information for these fields, but also to change the categories and tags for the listing. We are just telling him that it's a quality assurance expert and it should consider the user's feedback. So we define the agent by providing a model, the system prompt, and here as result type, we provide a list of AI agent listings that, again, here we are using a very bad practice that it's defining the class for this agent the same way we have defined it before. So remember, never use similar names. And actually, we could import this class from the listing classifier agent, because in the end, it's the same class. I have it like that because when I was building this system, I was running each agent independently. But once you put all these agents together, you really want to make sure that you are reducing redundancies. This agent will return a list of AI agent listings, and here we are providing two tools, one to get the categories and one to get the tags for that category. These tools are exactly the same as the ones we have in the listing classifier agent. The main difference is that for the listing classifier agent, this was not a tool. This was a static function that we were calling to generate the prompt. So this way, we are providing the categories in the system prompt. The reason why we are not doing this here is because sometimes the user will provide feedback that is just change a name, change a description, and it's not required to change the categories. So we don't want to saturate the prompt, and we only want the agent to have information about the categories when he's required to change the category. This is why we are just providing this optional tool that the agent can use. And that's it. This is similar to the other functions. And here we are using this database connection that we defined here. So we have, in our case, we are using a Postgres database. So with this function, you are connecting to the database, and then you can later use it here to perform the operations that you want. Now let's see the final agent in the flow. This is the DB inserter agent. This agent is responsible to insert into the database all the AI agents listings that we'll receive from the feedback router. The agent itself, it's quite simple. On the other hand, the tools that it's using to perform these operations are quite complex. So as you see, we define the model, we define this small system prompt, and we just tell that his output should be an insertion result. That is basically whether the insertion was success or false, and the name of the agent that it has inserted. So this is the agent, and as tool, we only provide him one tool. And we explain him what each of these parameters should be in order to perform the operation. Here we do some parsing from the arguments that the agent will pass in the function into a format that we specifically want to perform the insert in the database. This function is quite long, but at the end of the day, it is just inserting all these arguments into different tables in our database. As said, this will depend heavily on the schema that you have on your database, but it's quite useful to understand the way it works. You have an agent, you tell him that his task is to insert something in the database, and then you provide him a tool that performs this operation, and you explain him all the arguments that it has to provide to the tool. And that's it. In the end, all this code is deterministic, so it will be executed the same all the time. Great, so now we have all the agents defined, and now we come to the last part of the implementation. So it's about connecting the different agents so they are able to pass information from one to the other. And this is where LangGraph comes into place. If you have a look at the main graph, the way LangGraph works is, first of all, you have to initialize a state graph object. And the state graph object, it's just a state that the flow will have. And in our case, we have defined this state as following. We want to keep track of the latest user message. We want to keep track of tools. We want to keep track of potential AI agents, and we want to keep track of summarized agents and AI agents. The reason we are doing this is because when we initialize the graph, the first time we execute it, it will be empty. And every time that a new agent is executed in a node, we will keep adding information to the state by filling these variables. So for example, the first time we execute the graph and we send him a message, we will store in the state the latest message the user has sent. Then when the search agent is executed, we will store in this variable the tools that he has identified. When the filtering agent is run, we will store in the potential agents variable all the listings that he has identified. And we'll keep doing this until the end of the flow, where all these variables will be initialized and will have some value. In some flows, actually, you define just two variables and you just keep updating the same variable all the time. But here, for the sake of debugging purposes and observability, we have done it this way. Every time a node is executed and consequently an agent is run, we can check the state of the graph and see what action has this agent performed. With this state defined, we can now proceed and define our graph. You use this function to initialize a graph, and now you use the add node function to keep adding all the nodes that we have in our graph. So we'll define one for each agent: search agent, listing filtering agent, summarizer agent. And this is the name that we'll see in the node of the graph. And then the next parameter is the function that will be executed when this node is triggered. The cool thing about LangGraph is that these functions will have access to the state and will be able to update the state. So in our case, each of these functions contain the agents that we have defined before. And once these agents have finished being executed, we will manually update the state of the graph according to the results that these agents have provided us. The next thing that you have to do is to connect these nodes. So you have to decide what's the order of execution for the nodes. So this is done using the attach function. And here you are just saying, when we start, we go to the search agent. After the search agent, we go to the listing filtering agent. After the listing filtering agent, we go to the summarizer agent. and so on. The interesting part here is this add conditional edge function, that it is useful when you are in a node and you are not sure what will be the next node, and you want to execute one node or the other according to some criteria. And in our case, from the feedback collector node, we are going to use a function called root user feedback, and we will call either the listing rectifier agent or the publisher agent. Actually, this function will execute the feedback router agent that will return either rectify listing or insert listing. And this way, LangGraph knows whether the next node to be executed should be either the rectifier agent or the publisher agent. So this is the way LangGraph works. In the beginning, to be honest, it's quite complex, but once you understand the structure, you are able to build very powerful agentic systems. All right, so now that we have seen how it's the structure of our graph, let's go to each function that will be executed in each node. So in the search agent, we have this function here called search tools. And all these functions of each node work the same. We define a function that can access the state of the graph at that point of the execution. So for example, in the search tools, since it's the first node that is executed, we can access all these variables, but in the end, all of them will be empty except the latest user message. Then here you can ignore this part. This is an object that is used to write things in the Streamlit UI. We'll later see it. But the important stuff is this variable here, the state. And what we will be doing all the time is to import the agents that we have defined in this folder over here, and we are going to run them passing a prompt. In this case, for example, for the search agent, we are just running the first message that the user provides. So normally this message will be, please provide me the tools in the last article published, for example. So now this agent will be executed, and once this agent is executed, we can access the data of the output data that, if you remember, for each of these agents, we have normally defined an output, okay, an output type. And this output type here will be a list of tools. So in our graph, when we access this result, we will have this list of tools object. And now this is where we update the state of the graph. So when you are defining a function in LangGraph, you can easily update the state of the graph by returning a JSON with the key that you want to modify in the graph and the new value. For example, here, once we finish executing the first node, the tools key in the graph state will have all the tools that this agent has identified. So then we go to the second node that, remember, we have defined the order of nodes using the edges. And the difference here is that we create a dynamic prompt explicitly saying what are the tools. So here we access the state and we get the tools that we updated here. And here we just do some logs in our console and we write some stuff in the user interface of Streamlit. So this way we give this feeling of dynamism to the user. We execute the agent with the prompt. Here we are just communicating in the user interface how many agents we have filtered out of the total tools provided. We also provide information about the agents that we have identified. But the most important part here is this return statement. We are again updating the graph state, and we are filling the potential agents key with a list of potential agents that this listing filtering agent will return. And remember, this is possible because we have matched what this agent is returning as output type to this output type in the flow. If you don't have this match, you will run into type errors. So if we have a look at the listing filtering agent, it provides a list of potential AI agents. And here, in the potential AI agents, we again accept a list of potential AI agents. And that's it. We'll be following the same structure in each of the nodes. In the summarize AI agents node, we will take all the agents in the potential state, and for each agent, we'll run the listing summarizer agent. So in the end, we are running multiple times a summarizer agent for each of the different agents. Because here you have two options. Either you can provide the full list of AI agents to the listing summarizer agent, and this might work when you have one of two agents, but if you have 3, 4, 5 agents, the quality of the summarization will decrease a lot. So the best way to do it is to run this agent multiple times for different listings. This way will ensure that for each execution, the agent is 100% focused on one agent only. Again, here we do some writings in the UI. We will show all the information extracted. Here we update the summarized agent's key of the graph state. I will repeat myself, but I want to make it very clear. Summarized agents accepts a list of AI agent listing. We have to make sure that this variable that we are sending here to update the state is of this type. So this is why we have defined here list of AI agents listings. And if you remember, if we go to this listing summarizer agent, this agent will return for each run a specific output type that it's AI agent listing. We have it here. So this way, in our graph, we'll be executing this agent multiple times, and we'll keep building these summarized agents. As you see here, we are extending this list. We are adding for each execution a new agent. Now we go to the fourth node, where we will be classifying the agents. We do the same. We want to run the listing classifier agent once per each agent of the list. We print a confirmation about how many were classified. We provide some information about the category, the tag, and the confidence scores. And we update the state that this AI agent state will match this type, listing AI agent. So now after classifying the agents, we need to get feedback from the user. This node is basically using the human-in-the-loop feature of LangGraph that works pretty well. And this is something that you can use a lot of times when you are building automations, because in the end, you don't want to give 100% automation to the agent. You want to have some kind of sanity check. You want to approve a certain type of action before allowing the flow to proceed. And this is the case that we are using here. We want to make sure that before inserting listings in our database, a person gives the OK. The way it works, basically you have to use this interrupt function that it will post the graph, and it will stay post until somewhere else in the code we decide to resume this graph. We'll later see it in Streamlit, but this is done here. By combining this interrupt function together with the command resume, you can pause a graph and then you can resume it passing an input to the graph. If we go back to the node, once this node is executed, the graph will pause, and then it will be waiting for the command resume, and will store in the user input the value that we pass to the command. And then with this value, we can update the state. In our case, we're going to update the latest user message key. I hope this makes sense. It's one of the most tricky parts in this flow. It took me a while to figure out, but you have many tutorials out there and you have many videos that will explain it far better than me. So I totally encourage you to have a look at these videos and also to the LangGraph documentation. And just the last point here is when you're using interrupt function, you have to use memory in the graph. That this is another feature of LangGraph that allows you to store the state of the graph when interrupting the process. And that's it. So now we have some user feedback about whether he wants to proceed to publish the listings or he wants to rectify some listings. So now we'll use this root user feedback function that, if you remember, this is the function that we are using in this conditional edge. This function itself, you don't explicitly see it in the graph. You just see these conditional edges in the dotted line that exits the feedback collector loop. Here, what we are telling is from the feedback collector node, call this function, and this function will return the name of the node that will be executed next. You can actually, in the root user feedback function, you can actually return specifically a name of the node, and this way it's not necessarily this part over here. But if you're not returning the name of the node, but you're returning another key, for example, in our case, we are returning just rectify listing or insert listing, this next argument allows you to match the literal that the function is returning to the next node to be executed. And this function is just using the feedback router agent. It has this prompt about deciding what's the next step to be done. And here we are sending the feedback of the user, that is this input that we have here. So now the agent has to decide whether returning rectify listing or insert listing. And now here we are just again explaining in the Streamlit interface what we are doing. All right, so now imagine that we don't like the information that the listing summarizer agent has obtained, or maybe we want the agent to classify the listings in a different category or assign different tags. So this feedback router will route us to the rectify listing node, that this node is using this function over here, the listing rectifier. Here we pass both the user feedback, accessing the state, but very important, we also have to pass the agents that need to be modified. That remember, the listing classifier agent saved in the state these agents into the AI agents key. That's why here we are accessing this list of AI agents and provided in the prompt that the listing rectifier agent will take. We are running the agent, we are getting a result. We are printing again the rectified listing information in the Streamlit UI. All these are prints. And then, very important, we are overriding the AI agent state key. At the beginning of the node, if we access the AI agent's key of the state, we get the listings before correction. But then, at the end of the node, we are updating this state with the rectified listings. So now, once this node ends up executing, we have defined an edge that says, always, when the listing rectifier agent finishes, go back to the feedback collector. And this is how we build this endless loop that if we want, we can be indefinitely asking for rectifications in the listings. We will not leave this loop until we explicitly say, hey, we want to finally publish these listings in the database. Imagine that now we are fine and we said, okay, please proceed. The feedback router will redirect to this node over here that uses the function insert listing. We will just import the DB inserted agent, and we will create a loop that for each of these agents that we have in the state AI agents, that remember, it will be either the state that we have immediately after coming from the listing classifier agent if we are fine and we don't want to rectify any listing, or the state that we updated when coming from the listing rectifier agent. So in both cases, we will create this loop and we will try to insert each agent to the database. Then we'll get the results from the inserted agent that, if you remember, we explicitly set the result to have a success key and a name key containing the name of the agent and whether the operation was successful. And now we are printing all this information in the Streamlit UI, and here the flow ends. And that's it. This is the graph. Some stuff might be a bit difficult to grasp at the beginning, especially when working with LangGraph. But once you master these concepts, trust me that you will be able to build very powerful agentic systems. Okay, let's now go to the app interface. And as said, we are going to use Streamlit, and we have here the file for Streamlit. We have a main function that basically is printing stuff in the chat, and at some point is asking for a user input. If we have a look at the input, in the end what it's doing is running this function that it's run agent with streaming. And this is where the logic of running LangGraph lies. We are creating a thread ID. So a thread ID is used in LangGraph in combination with the memory that, if you remember, I briefly mentioned here in the main graph at the end, that we created this memory and we are creating the graph with some memory. So normally you would store this memory in a database, so then you can later access it. But the state of the graph will be stored in our local machine during execution. But whenever we kill the terminal and we stop execution, this memory will be lost. In any case, if you're using a thread ID in combination with the memory, it allows you to run the same graph multiple times with different users, but for each user, reference the state of the graph that belongs to him. So put in another way, an agent is running the graph, it's creating some state, and you're storing this state in a database. Later, imagine that the user closes the session and comes back. Whenever you invoke again the graph, you can reference this thread ID and then go to your database and fetch the state of the graph. And this way, the user will continue to execute the graph in the point where he left. And this is what we are doing here. We are creating a thread ID. We are creating this config object requiring LangGraph. And when we execute the graph, that it is done here with this function graph stream, we are providing first state of the graph. In our case, remember that the state was this one. agent state, we'll initialize the latest user message to the input of the user in the chat, and we'll leave all the other fields empty. But then we are also passing this config that has this thread ID, and this way we are able to know to which execution we are referencing. In the second parameter, we are passing this configuration object, and then in our memory, we'll store the state of the graph under this thread ID. And later, when we interrupt the graph, remember that we have a node where we provide feedback, we'll be able to resume using this command function, but also passing the same configuration object. So this way, we'll keep referencing to the same thread ID. If you don't add this thread ID and you don't add memory to the graph, you will not be able to create a graph with human in the loop. So remember, you have to create a config object, assign a thread ID, make sure that the graph has some memory saver, and finally, you are initializing for first time or resuming the graph after calling interrupt. You have to make sure that you pass this config with the same thread ID. And finally, we are using this optional parameter called stream mode. This is something very particular when using Streamlit together with LangGraph, and this allows you in each of the nodes to use this writer to send messages to the Streamlit interface. So now before running the agent, I want to show you how the graph looks like. And to do that, we are going to use a tool called LangGraph Studio that allows you to visualize the graph that you have built here. Actually, it's the tool I'm using all the time to show you the graph. I'm going to show you how to run LangGraph Studio because it's quite useful. First of all, go to LangGraph Studio and install this package. I already had it installed. But then something important to run LangGraph Studio is you need to have this LangGraph JSON where you have to indicate where the environment variables are located and where the agent is located. You have to place the name of the file where you have defined the graph and also the object that will have this graph. So this object over here should match the graph compiled in your LangGraph file. With this, if you go to the terminal and now type LangGraph dev, this will open a new window. Then here you will be able to see the graph that you have built, the different nodes, how each node is connected to each other, and you can actually run it. For example, remember that our first node, the search agent, is expecting a latest user message. Here we can say, give me the last tools, and the node will start executing. And something very cool about LangGraph Studio is that you can see at all time what was the state of the graph after executing each node. So for example, here we have started the graph and the state was the latest user message. Now after running the search agent, the state here, we see that we have as latest user message, the same message because we haven't updated the state, but the tools now, we have many tools. Then when running the listing filtering agent, we see that we have a new key called potential agents added to the state. So out of these many tools, the listing filtering agent has decided to only keep 2. And now the summarizer agent has filled, has filled the summarized agent's key with all the information for each agent. So remember that we only had 2 agents. And then the classifier agent has updated the AI agent's key of the state, adding the category score and the tax score here. So now when reaching the feedback collector node, remember that you have this interrupt function, and as we said, LangGraph is waiting for the command resume in order to resume the graph. So it provides you easily a way to call this command from this interface, but in our application, as you remember, we are going to call this resume from here. With this manually, we are calling command resume with the user input. But here, since we are not, right now I'm running this graph without a Streamlit, so the way to resume this graph will be to provide a JSON file here with some feedback. The only way to provide input to the resume command is using a JSON file, so you cannot just type here, for example, your feedback. As you see, there's an error message here. I haven't found any other way to do it unless you specifically provide a JSON object. So this is what we are going to do here. Here what has happened is the feedback router agent has read this message, please rectify listing, and has redirected the flow towards the listing rectifier agent. And remember that the listing rectifier agent will take this feedback and also these AI agents over here from the state and now rectify the agents. We haven't provided specific details about what should be rectified, so the agent hasn't done anything. But here we can say, for example, imagine that in the name of Chris, we want to add the AI word. Let's say feedback. So now the feedback router has detected again that we want some rectification. The listing rectifier agent will, okay, we see it here. You see now, Crisp AI. In the previous iteration, it was Crisp. We have gone to a feedback collector agent. We have told the agent to add AI to the Crisp name. And now this listing rectifier agent has updated the state to include the AI inside the Crisp name. And now imagine that we are fine with this rectification. Now we can say proceed to insert. So now the feedback router agent knows that we want to insert this into the database, and we call the publisher agent. Actually, if we go to the terminal, we can see what's happening behind the scenes because I have created some logs in the code. And for example, we see here that it has already inserted the Crisp AI into database. And now it's inserting agent Quen to Omini. And this is all the information for Quen to Omini. Okay, and it's here. It finally inserted this into the database. And here the graph has finished. All right, so now that you know how to run your graph in LangGraph Studio, let's see how we can run Streamlit. So this way, instead of just interacting with the graph in LangGraph Studio, that it's not very user-friendly, we can do it with a nice UI. So here you'll have to install Streamlit in the get started, and you just install Streamlit. In my case, I have already installed it, and now you just execute this command to run Streamlit. So now we're going to see a demo I have recorded offline, and what I've done is I put on the left the interface of Streamlit, and on the right you're going to see how the graph executed in real time. So we are going to be speaking with the chat interface, and you will see how the different agents will be executed. So let's have a look at it. We are going to tell the agent to publish some listings. Now the search agent will come into place and will detect potential listings to be published. We see here all of them. The listing filtering agent is taking all these listings and only taking those that are real AI agents. So in this case, it has identified 3 with confidence scores of 95, 92, and 90 respectively. Now the summarizing agent has taken each of these real AI agents and extracted all the information that we wanted. As we see, we have the features, pricings, use cases. Now the listing classifier agent has assigned some categories and tags to each of the listings, and we see the confidence scores. The graph is waiting for our feedback. What I've told the agent is that we want to remove one feature from EraserBot. In this case, it's going to be centralized documentation. And also we are going to change the category for MeBot. So now the feedback router has directed the flow towards the listing rectifier agent that will take this feedback and will modify the proper listings. And here we go. We see that for EraserBot, it only has 4 features. It has removed the feature that we wanted to remove. And now the category for MeBot has changed. It's customer support. The feedback collector is waiting for our input. We ask to publish the listings, and the feedback router will give the green light to the publisher agent. It takes all these listings and it publishes in our directory. It has published the 3 listings, and now if we go to our directory, we see the 3 new listings. We see Faithom, we see MeBot with a new category assigned, that it's customer support, and then we also see EraserBot with only 4 features. So centralized documentation feature has been removed, as we said. Alright guys, I hope you enjoyed the video. If you did, please leave a like and subscribe. My idea is to keep publishing videos of the learnings that we are getting from building projects for our customers at Flowhog. Flowhog is an AI agency that helps SMEs automate their internal operations using AI. If you're a business owner or you work for a company that has automation needs, contact us at flowhog.com. We'll be happy to help you.